Hi, in this video we will talk about how to simulate a synthetic aperture radar using Ansys PerceiveEM, which is a GPU-based SBR solver which call or run using a lightweight Python API. Before going into the demo how to do that simulation, let's understand what is synthetic aperture radar. It's a method to create an image of some particular target where the radar can be equipped on an aircraft, drone, satellite kind of object where it will be moving and the target are assumed to be stationary or it can be moved also. What you will see is there is an aircraft which is trying to send signal, and depends on the material property, the signal will be reflected back to the radar. There are a few things which you need to understand before going into SAR. So for example, my antenna is over here. If I look directly below the target, I will not get any image because it will be acting like an altimeter radar, which will give you just a spot telling that the distance to the antenna or the platform to the ground is this much of distance. But if you are looking with a side angle, then you will start seeing different reflection from different range compared to the look angle. Look angle is the angle which will make between the normal to the ground and the angle in which the main lobe beam is focusing. The swath of the radar is nothing but the area at which the beam is going to cover, so that the reflections which is coming back to the radar is actually the reflection from this area. So based on your swath size, your resolution changes, the bandwidth of the radar also changes with resolution. Your look angle also matters sometimes with the resolution of the target. And your radar in this case normally moves on the platform. So there are different types of SAR imaging. We will discuss that in a very simplified way. The first one is called the strip map SAR. How it is working: the beam is fixed at a broad area, continuously illuminating a strip of a terrain, as with either with a satellite or a aircraft. So I'll send a one pulse, then I'll move my satellite to another location, send another pulse, then send another pulse. So this create a multiple reflection from the terrain, and after that you can create an image out of it. That's a strip map SAR. The problem with the strip map SAR is the resolutions are typically 3 to 30 meter. If somebody want a high resolution image of some particular area, so they use a Spotlight SAR where a gimbal or a phased array will be equipped over here, and during the flight path of your aircraft or satellite, you will always pointing to the one particular location. So I'll point here, first pulse, second pulse, third pulse, and up to n number of pulses, always illuminating this particular area. That will help me to get a high resolution image, sometimes millimeter to centimeter level image, depends on how much bandwidth and operating frequency and other concerns you have it. So it's mainly used for imaging cities, military surveillance. You can actually image some of the objects on the terrain very nicely and able to detect these targets from the radar. Another few more SAR imaging methods are there. SAR, which are also kind of working similar to the strip map SAR, where while going these area, instead of looking only to one particular area, you can look each pulse to different areas on the terrain and then create image out of it. So there are different techniques. Normally this resolution of these SARs are lower compared to strip map, because you are switching your beam to different location on the terrain. But with the new techniques, with the different adaptive beam formings, you can create a very high resolution also using the this SAR operation. And this is mainly used for imaging really big area. Sometimes kilometers of hundreds of kilometers area SAR imaging you can do it. One more method is sliding Spotlight SAR, which is used in Sentinel-1 satellite, where I can image one particular area, then on the go I will go and switch to another area and then create a map which will generate a really big area for SAR imaging. Based on this image, whether you are transmitting which kind of antenna, whether are you transmitting horizontal or vertical polarization, which antenna polarization you are receiving, you can generate these images and interpret a lot of things. For example, polarimetric SAR, you may have a different type of antenna. For example, I can transmit vertical polarization, receive vertical polarization, transmit horizontal and receive horizontal, transmit vertical, receive horizontal, or transmit horizontal, receive vertical. You will get a different type of reflections from terrain. For example, the buildings and other thing will have a very good reflections from horizontal polarization, as well as vertical also is pretty good for getting a surface scattering, smooth water scatterings and other thing. But when it comes to volume scattering, especially the leaves and vegetations, where you have a lot of even though that may be a few meters height, there are objects which are smallly vibrating over the time, and that has some volume in it. So this cross-pol SAR, especially VH and HV polarizations, are widely used for detection of forest area and agriculture, and camouflage detection, especially if you want to hide something beneath some object. That is cross-pol SARs are pretty efficient. So it has a wide operations, wide applications are also. And another type of post-processing of this SAR image is called interferometric SAR, where I will scan a particular terrain today, and I will scan after a week or next day, and then compare these two SAR with different times. Maybe these two SAR image may be taken at different distance compared to the initial imaging point. If you compare this image on top of each other, you can actually create a very good terrain maps. So it's called digital elevation models, and also can be used for determining the deformation happened because of the landslide, earthquakes, and volcano effects. So this is mainly used for such application. These are some of the main area or main application of SAR imaging. Now we will see how we can use this simulation to create this SAR image more realistic way. Before starting the simulation, you need to import or you need to export the CAD of a terrain, building, vegetation, water body, everything into an STL or OBJ file format. So I created a YouTube video. You can search it in YouTube, which will show you how to select a terrain anywhere in the world, export a building terrain, all the information into STL. So watch this video. It will show you how to export those CAD models, and we'll use that CAD model for the EM simulation in the next in the current video. Now in this particular folder, you can see my building, roads, terrain. All these STLs are there. I'm going to use only the building and terrain for the time being. What I need to do first is I need to create a text file in a JSON file format. The format will look like this. So this is something called creating an asset. I'm telling this is a HL area, and I have a terrain. So just mention this is a terrain 1. Going to like render using purple color, and material will be earth rough material. And now I have another STL, which is building STL, rendering using a gray color, and concrete rough material I'm going to assign. I want to move this terrain by 22 meter down from the initial position, that just to make the things, some of the aircraft model to be arranged. That's the only reason. And this the color is just for rendering the in PyVista, not for EM simulation. So you might have seen some material property which is mentioned here. So I'll explain how to assign the material property. So if I go here, you will see the same JSON file. Here is a material. Here in the material, you may see some property, for example, earth rough, which is having a, let's go with the earth first, which is having a thickness -1. So -1 thickness indicating an infinite thickness, especially for terrain, you will have an infinite thickness. What is the real part of permittivity? Imaginary part of permittivity, real part of permeability, imaginary part of permeability. What is the conductivity? And a coating index is a index number 1, 2, 3, 4, 5. You will see here, but these are the electromagnetic material property. You can assign, it's a text file, you can edit a different material property. Some of the the material will have some roughness. For example, terrain will have some kind of roughness, where you can set the roughness parameter 0 to 0.5, and what is the standard deviation of the roughness in terms of millimeter. Sorry, this is in terms of meter. 0.3 meter roughness is there in the terrain. Same way I can assign concrete. Concrete also having an infinite thickness, especially for a wall. Or if I want some specific thickness, I can also specify here. Example, if you take a glass material, I have a thickness of 4 mm thickness. This is in millimeter. Give a note on it. Permeability of 5. Imaginary of permittivity is sorry, this is a permittivity, real and imaginary, and permeability. And there is a small conductivity which indirectly turn into your loss tangent. The other side of this 4 mm thickness is a vacuum. So when the electromagnetic wave is hitting, and it's going to penetrate through that 4 mm thickness and going the other side with a vacuum. There are some radar absorbing planes where I can select the aircraft body and say this is a permeability, permittivity, conductivity of that absorber, and instead of a vacuum I can say PEC. So that means the other side of that is a metal. There will not be any penetration, the ray will be reflected back. So that is how. Same way I can assign for vegetation, plastic, aluminum, rubbers, and so we have created a set of material properties here. You can choose, or you can edit it, the material property, or you can add it also. So this is how we create that the terrain, and just created a JSON file. Same way I also created some aircraft models. You can see there is a A380 aircraft model, and if you go inside you will see same thing, and there is a A380 STL, and there is a very small roughness based aluminum. So I can remove the roughness, but I can, if I want, I can add a roughness also to that aircraft model. So like that I have a couple of aircraft, couple of terrain and building information. Let's go back to the code. As I mentioned, this is a GPU based solver where I can run using a simple Python API. The slant angle, let's go through the code how it is written. So this is the slant angle. Slant angle means the look angle, at which angle your radar is looking towards a terrain, and height of my nadir height, especially that is what it's written, 25 km above the surface the aircraft is located. I want to create an image in every 1 degree resolution for a 360. So it is something like an airport with the multiple aircraft. I'm going to fly my aircraft 25 km around that one in a circular path. Here I can tell how many electromagnetic reflection has to be considered, because this is the SBR technology. I can say 3, 5, 10. There is no limitation here. GPU will take some more time to come. I can go with the 3 or 5 for the time being. And if there is a transmission race, for example, some of the aircrafts having a glass windshield and other thing which the electromagnetic wave will pass through, transmit through, then I can enable this ray also, like 1 or 2, but I'm not using any such material for this particular application, so that's the reason I kept it 0. Now these are the operating waveform of your radar. For example, I'm going to work on an X-band. 10 gigahertz is my center frequency of my radar. I have a range resolution of 1 meter. I want to create a 1.5 kilometer by 1.5 kilometer area. That's the reason SAR range and cross range is 1500 meter with a resolution of 1 meter in range and cross range. So that determines the range resolution determines the bandwidth required for your radar, and the cross range determines how many azimuth angle you need to scan, and also determines how many pulse you need to send it. So the back calculation of bandwidth and aspect angle will be computed based on your input, and number of frequencies in the current processing interval also will compute. You can specify your antenna beam width, or else you can use a simulated or measured antenna pattern into the solver. Then what I'm doing is, in this particular code, I want to capture only 800 meter around the HAL airport area. That HAL airport JSON file I'm loading. Same way I'm also loading my A320 Boeing 747 A380 Cessna aircraft and Gulfstream aircraft into my scenario, and those aircrafts are going to separate by 300 meter in the runway. That's a code it's doing, and this is used for rendering that scene in PyVista. Now I will run it, and this is the waveform I'm using. I'm going to use a pulse Doppler or range FMCWM or LFM radar capability can be simulated. Then coming back here, I'm adding my antenna where I can specify I want to use a parametric antenna where you can specify what is the horizontal and vertical beam width, which is 10 degree beam width here. And you can also specify whether you want to have a vertical polarization, horizontal polarization, or RHCP or LHCP polarizations. You can write it, or else instead of parametric you can also load file based like FFD, which is coming from HFS's far field data after your antenna simulation. You can use that pattern also here. That will give more fidelity on your SAR simulation. Then this will add this antenna as a transmitter and receiver over here, and this will tell you which GPU you are going to use and how much percentage of RAM you are going to allot for the simulation. The number of ray batches is nothing but, for example, 1 million of ray going to shoot, so that's going to divide into 500 batches. So that mainly to reduce the memory consumption of GPU. If you have a lesser GPU, you can try it, but it depends on the area and the frequency of operations. You need to have a higher GPU. So I'm going to use a 45 GB GPU for this simulation. And here during the simulation, it will render one more time the graphics. We do have option to change the side lobe level once the data is received or computed. I can say whether I need a no window in the on the IQ data, or do I need to add some windowing which will smoothen up this image of the SAR. So this is a solver will kick up here. So this solver will run, result will come here. We are actually generating ISAR image out of it, and every 1 degree I'm also saving this image in like image 1 2 3 up to 360, so that this image can be used for generating or training the AML model for later stage. And this is what this code, very simple code. Let me run this solver. So clicking here, first it will run, it will load all the terrain, aircraft, place it and render it. So that is what happening. So normally this PyVista will take time rather than solver. So this is a area, so this is 800 by 800 meter area, and this is Airbus 380, and this is Boeing 747. This is Airbus 320 on the back side. Over here you may see a small aircrafts which are this is a Cessna aircraft, very small, and there is a Gulfstream aircraft also. And you can also see the buildings which is placed here. And let me run this solver just to verify whether the CAD are aligned properly as expected. I can just close it. I'm using an NVIDIA L40 GPU card, and you can see these aircraft models. There is a Airbus A320, Boeing 747, 380, a Cessna, and Gulfstream aircraft. And these are the building reflection which is coming up. You can see there is a strong reflections from the building edges. Those are because of the mainly because of this building sharp edges that creating that high spot. And this can be reduced and the image can be even smoothened out if you apply some windowing function. We'll run one more case with another window. Let's run the simulation with another windowing function. What I am going to do is here I'm going to enable this and disable the flat windowing. That means no windowing function. So let's run the code one more time. Now here you can see your image become more smoother. Your buildings are very clearly visible. Your aircrafts are also visible. I can use vertical, horizontal, 199 vertical and horizontal, then you will see another set of images. So this is about how to create a SAR image using this GPU solver. So while these SAR images are creating in an output folder, you will see the images are also saving. And finally, the one video also will get recorded. So for example, if I open this particular image, you can see this is taken at 82° and how the SAR images of that aircrafts are coming. Like that, the data are saved. You can use it for AML target classification algorithm generation in the later stage. One more thing which you can notice here is I'm generating the SAR image of this scene and saving as a JPEG in that same code. So which can be used for every look angle. You can see this SAR image for look angle with a 4-degree. So during the simulation in an output folder, you will see these images are getting generated. These images can be used for AML training in the later stage. So while these SAR images are creating in an output folder, you will see the images are also saving, and finally the one video also will get recorded. So for example, if I open this particular image, you can see this is taken at 82-degree and how the SAR images of that aircrafts are coming. Like that, the data are saved. You can use it for AML target classification algorithm generation in the later stage.